Hello, my name is Shazeb Suhail, and in this screencast, I'm going to be going over our memory management assignment in this operating systems class. So we'll start off by going over the code, and we have a couple supplemental functions we use in this program. We have our print binary function, which is pretty simple. It'll just print a decimal or hexadecimal number into 16-bit binary. We have a get random number, which is going to be useful later on in the program when we're trying to randomly select virtual page indices and map it to page frames in the physical address table. And then we have a press enter, which is just to pause execution of the program for the user to read what's going on. Basic format spacing for some of the output that's going to be printing to the console. And then we have our main method, where we'll start off by asking the user for a page size. Page sizes is either going to be 4K bits or 8K bits. Then we'll go ahead and print out the page size in binary and hexadecimal formats. Then we'll move on to actually creating the virtual page, and we do that by taking the virtual memory size and dividing it by the number of bits we've chosen for the page size, which will determine how many virtual pages will exist. And we'll do the same thing for the physical memory size. We'll divide it by the page size selected, and we'll come up with the number for how many page frames will exist in the physical address space. So this portion right here is creating the virtual page, and I'll show that in code once we begin program execution. And this second algorithm is a little bit more complex, but to kind of simplify what's going on, if you see this image that was in the textbook, you see how here's our virtual address space, which is going to be much larger than our physical memory address. Same in our program. But the main important thing is you see how they're randomly mapped to different page frames. That's exactly what's going on in this part. I'm just choosing random numbers or choosing random virtual page indices, and then I'm trying to map it to a page frame. And so I'm trying to do this without any duplicates. And once I actually print out this table during program execution, we'll see much more what's going on. Then we have our last stage of our program, which is going 10 times. It's going to ask for a hexadecimal, and here's how we'll basically debug and make sure our program is working correctly. If we're able to determine that the virtual page has been mapped, it'll print it out. Otherwise, it's either going to say currently on disk, and if we choose a number that's completely beyond virtual page size, it's just going to say that virtual address is out of range. So let's move over to program execution and begin this. So I'll use my compile script. So you can see it's going to first ask the user for page size, 4K or 2K, 4K or 8K. I will go ahead and go with 8K because it'll make for smaller tables, easier for us to check out. So this is going to be the page size in decimal, 8,191. Now this is actually the limit for how much it's going to do, but it should actually be 8192. But if you print it in binary and hexadecimal, this is what it's going to look like. Now because we have 1 million bytes of virtual space and 512 bytes, 512k bytes of physical address, we're only going to get 64 page frames out of that. So let me show you exactly what the virtual address space or virtual pages will look like. So you can see that because we include 0 in computers, it's going to go from 0 to 1 less than the next page frame. So then continuing, and if you look at the numbers, it should be accurate, and you can see that it is 128 pages, and it goes up to the 1 million bytes that we have determined. And now for the physical address space. So these are the page frames. Now, not only is each page frame have a virtual page index, so when it says 95, it's referring to index 95 on the virtual page. So this virtual address space is mapped into this physical memory address space. Same with all these, you can see they're all random, none of them are duplicates, and it's just all randomly selected. So for this, I'm gonna have to use the programmer calculator to really explain what's going on. So let's just start off with this first one right here, 95. So if I go to 95 and we go to indice 95, you can see that it exists within this range. I'll open up the calculator, I'll go to the decimal portion, and let's just write this first number down, 778240. So this is basically the first address space in this range. If I take the hexadecimal, it is BE000. So let's go ahead and write that down, BE000, and let's see what we get. So it's going to say that virtual address exists on virtual page 95, which is true. That's what we're going for. And that the virtual page is mapped to page frame 0. As you can see, perfect. This is all going. Now, without looking at the final result, we should know that it should map to 0. Even though on the virtual address space it's mapped to 778240, it should land upon 0 right here. If I go here, we should see that boom, it does land on hexa 0, which is 0 decimal. So it does exist as, well, it is mapped to the physical address. So that's perfect. So if I try this again, now to continue, let's try another range. We'll do address virtual page 95 again. We'll go check out 95. Here we go. So we have this number here, which is the end range. Now based on what we've covered so far, this should land exactly at 8191. But I'm going to show you that offsets work as well in here, that is able to correctly determine what's going on. So instead of 786,431, this should be the end range. But what we're going to do is we're going to minus 1. Right, so now we get 430 instead of 431, and this will be BFFE. So let's go ahead and insert that, 3FFE. Now let's see, and I might have messed up. Was that the right one? Oh, I put 3, sorry. BFFE. Now you can see that it is still on virtual page 95, which is still frame 0. And if we look at it, it should be 8190, one less than the end range, which is perfect. This is a hexadecimal version of it. Now what we're going to do is we're going to try to figure out one of these that is not mapped. And so I'll just try a random number like 28. So let's see if 28 exists on here. So far I do not see 28. So if I go to virtual page 28, so I have to pick a range somewhere between here. So it could be anything. I could just do 2293 instead of 76. I could do 79, and this becomes the hexadecimal version. Oh, whoops, maybe I didn't do that right. One more time, 229379. And it becomes 38003. So let's type that in, 38003. So you can see what happens is, as I was correct, the virtual address does exist on page 28, but it's currently on disk. And that's because it hasn't been mapped to a page frame. So that works, right? So all of this, if I was to pick something that was completely out of range, right? So we have this number here. Let's say, so decimal is 1048575, right? If I was to just add 1, which it makes it out of range. Well, actually, to make it a little bit more, let's add 50. So it'll give us a hexadecimal of 1000032. So let's try that. 1000032. You can see that you entered a virtual address out of range because it is way more than the end one. But let's try this one right here. So if I type this again, 1048575 decimal, which equals 5Fs. Let's type that down. 1, 2, 3, 4, 5. And you can see virtual address exists on virtual page 127. Now, do I see 127 on here? I do not. So this address space is currently on disk. So that's working. Now let's do one that's on, so we have 6 right here, right? Which is page 55. If I go to 6 virtual page, we should see it would land within this range. Let's go ahead and pick a number in this range. Let's just do 50,000 because it falls in there. And that's, there we go, 50,000, which is hex 50,000. Okay, perfect. Or unless I did that wrong. Sorry, I did keep doing that wrong. It should be C350. So C350. Check it out. We can see that virtual address exists on virtual page 6. Correct again. Virtual page is mapped to page frame 55. So let's check out page frame 55. Boom, that's correct as well. And it comes out to hexadecimal 451408. So let me just do a couple calculations to show you that this is indeed true. So we'll switch over here. We'll do decimal. Oops, 50,000 minus 49152 gives us 848 offset, right? So if I go down here to page frame, it was which one? It was 55. 55. So if we do this plus 848, right? Plus 450560. So the resulting answer should be 451408. So let's check it out. 451408. Perfect. Even the offsets are working as intended. So I'll just go ahead and clear this out, and I want to show that the 4K works as well. So if I pick 4K, you can see that this is the address size going to be up to 495 bits from 0, which is actually, in actuality, should be 4096. But the only reason I have it written this way is because it was written like that in the assignment. And now you can see that the amount of virtual pages has increased from 128 to 256, and the number of page frames have increased as well to 64 to 128. This is a virtual address space. You see it goes all the way up to 256 items, right? If we're including 0. And it's still mapped to the same end spots. The address range is just smaller. You can see 0 to 496, 4096 plus 8192. Boom. It's all working properly. Go ahead, do the page frames. You see it goes up to 128 page frames now. And I'll just do a random number, right? Let's just pick a random number, see if it exists. So let's do something like 363636, right? Which goes into 58C74. So 58C74. This random one, let's see if it's correct. It says it exists on page frame 88, which is mapped to page frame 45. Let's check it out. Page frame 45, 88, boom, perfect. And it would exist within this range. If I was to do all the numbers, calculations, all that, it would indeed be correct. And so everything's just working as intended. I created this delimiter of -1, which is a flag to exit the program early, so you don't have to do all 10 loops. And that's pretty much it for this memory management assignment. Thanks for watching.